I mean, okay. If there is at least one person who speaks English, we speak English, right? So we speak English, right? Okay, cool. Yeah, sorry for delay. So should I? I'll probably be jumping. All right. So a couple of organizational things. I'm really sorry to pack it, but basically this time I'm in Moscow only for a week, and that's why I suggested to have it the 6 lectures packed in basically in 3 sessions, 2 hours, well, and something each. And my plan is to have roughly an hour, a little bit more than a break, than another hour. A break probably for 15 minutes. Well, we can extend it a little bit, but I guess not the first time. So now, for those from Skoltech or maybe from Vishka, I don't know, who wants it for credit. I'm actually not sure if we arrange it for credit at Vishka, but anybody who is planning to take credits, Skoltech? Okay. Oh, okay, cool. Then basically plan is will be lectures, and then through lectures I'll be highlighting a number actually of well, if you wish, interesting subjects which I'll not be able to cover in depth, or subjects which are kind of open, and then by the last lecture we'll probably spend some time discussing who is speaking which subject, and then the plan is for remaining maybe months, and we will agree on details with those who will stay in this extra period. Plan is to have maybe, well, 2 weeks of, I mean, shifting for 2 weeks, not doing much for 2 weeks, but then probably having a once a week session over Skype, and the intent is that those who will pick those specific subjects, specific projects, will be presenting and then writing reports, right? So that's basically the plan. But we'll discuss it in depth by the last lecture. Maybe we'll start discussing it already after tomorrow. Okay, so right. So now, yeah. So I'm Misha. That's fine to call me Misha. I'm actually not used to any other longer name in Russian. So I'm at Skoltech. I'm also at Los Alamos. When I'm not at Skoltech, Los Alamos is a national lab. And I'm physicist by training. I was doing, quite a number of years, probably on a scale of 20 years, various problems which are on interface of theoretical and statistical physics, and information theory and computer science and machine learning computation. So that's how this type of course emerged. Actually, something of that type I already gave in Moscow. It was kind of joint Fistech Yandex in 2011. So probably neither of you attended. Actually, many things happened since. So it's renewed. So old notes and lecture, not lecture notes, PDF file is available on my web page. And that's actually the page, so you can find it there. I also, so now as the lectures progress, I'll be updating those notes, and actually they already significantly changed. I heard from Yura that there is at least one responsible person who will set up Dropbox, right? Dropbox or whatever other way to share. So whenever I'll get it, and hopefully others, let's maybe in a break organize ourselves and subscribe. I'll be dumping this PDF file updated presentation, and we'll be doing it basically before every lecture. I also have semi-organized notes. Actually, its intent was to write a review. It's still in progress. Well, I'll probably share some of that too at this Dropbox. So there will be some material. So now it's very well. I'm assuming, guys, that you know enough of math to digest it. Will be quite a lot of math. Those without mass background, probably you'll see if you can handle it or not. Physics background is not really required. In this sense, it is graduate course, so it's not a base kind of introductory course. Now, as you can see from the title, it's about graphical models. So graphical models I'll explain in the first lecture on examples, and will be, if you wish, formal formulation. However, well, I mentioned mass, but it will not be rigorous mass, so it will not be theoretical mass. So I'll not be doing proofs, even though many things which I'll be talking about, they're provable, and actually there are proof behinds, but it's not in this course. And it's not what I emphasize. Main emphasis is on intuition and on, how it, so basically intuition and maybe schematic ideas. Sometimes of proofs, but also of how to use it. Okay, so in terms of how material, how I break the material, you didn't see it in announcements, so I improve it a little bit. Improve in the sense, well, in some cases extended, in some collapsed, and it probably will be as we progress, and depending on the response from you. Probably will be some modification, but so 6 lectures, and you can read it, but I guess we'll go through all of that. So for the first lecture, first hour, I'll be discussing those graphical models. So I'll introduce them, and then there'll be some examples, and then we'll get to to how. Well, we'll set up problems, define what are graphical models, set up type of problems which you can solve or you can pose, and then we'll do some reformulation in terms of optimization. Actually, there's no need to take a picture. You'll get it on Dropbox, but okay. In terms of books, as I said, there are no perfect books on this subject, so it's really emerging subject. Probably the closest to book is the first one, so it's Martin Van Wright and Michael Jordan. It's much more on the mathematical side than what I'll be talking about, even though, well, it's balanced actually. And those two are quite, famous authors, and probably you've heard those names, or maybe you've heard, maybe not. They're both at Berkeley. It's actually available online. So all other books, they're kind of related. There are some materials from those books which overlap, but much less than the first one. Maybe in general, I really would recommend the second book, which is like a Bible. It's a big one. But it's a cool book. It's really broad, and it's much more popular, and for much broader audience than the rest. And the rest of this list, maybe this David McKay book is also, well, if there are physicists who are interested in this subject, probably that would be easy reading. David McKay, he unfortunately died this year. So he was a physicist by training, and this book is also interesting, Mezart and Montanari. So it's a book about a related subject, and it's more about explaining for those who are not physicists, and those guys are from so-called spin glass community entering in computer science, explaining for non-physicists what these physics approaches are, and how they're related. This is coding theory, and there's a lot of overlap in terms of applications, but not directly related. And this is again, for somebody from physics, that's actually very nice reading for introductory reading on optimization algorithms. So it will be, some overlap with all that. So now what is graphical model? And there are multiple ways to introduce graphical models, so there are different formulations. I'll try to stick to this one, even though especially discussing some examples I may deviate, and then I'll warn you. Oh yeah, and by the way, ask questions please if anything not clear. Exemplary graph. and graph consists of nodes and edges. Again, I'm not very picky at this moment in terms of definition. And then we define in this particular representation variables which reside at edges. For example, there is this variable which sits on edge 1, 8. Right, so connecting node 1, so I enumerate nodes 1, 2, 3, and 1, 8 is a variable. And I'll be, unless specified, I'll be talking about binary variables. However, well, that's default. I'll also be discussing some other alphabets, in particular continuous variables too. So those are original variables. I'll form from those variables, which resides on edges, vectors. And in particular, I can form a vector which includes all edges, right? And then I would usually use notation just sigma, like that, for this long vector. Well, in my notes, sometimes I put it like in bold, but then, I mean, it's a mess. So if sigma without index, it means vector and vector with components from all edges. But then, if index is, basically two vertices indicating edge, so like 1, 2, well, 1, 2 or 1, 4, like 1, 4 or 1, 8, yeah, so it's clear that's variable sigma 1, 2, sigma 1, 4, so it's either plus or minus 1, plus or minus 1, plus or minus 1. But then, if I put sigma with index 1, 1 is a vertex, it means that I form vector, and vector may be of arbitrary length, depending on what is the degree of this node in the graph. In this particular case, it's degree 3. In the case of vertex 2, it's degree 2, right? So, vector of length 2. That's in terms of notation. So now, what is graphical model? Graphical model is a way to represent probability distribution of this vector sigma, which is a vector, again, constructed from variables residing at each edge. And there are, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 in the power 10 possible configurations, right? Each configuration is assigned a probability, and probability is factorized according to this graph. That's why it's called graphical model. Sometimes it's called factor graph model. And factorization is written in this form. So it's factorized in the sense of its product. Product of functions which are f with index a. Functions are residing at vertices, and functions, I'm not specifying details of this function, only that they should be, well, because it's probability should be positive, and of course normalized too, but first of all positive, all those functions are taking positive, okay? Otherwise, it may be, reals, it may be integers. Now, obviously, probability should be normalized, which means that I need to introduce this factor z, which is actually key object in all the story. It's called partition function. That's how it's called in physics. Actually, in Russian, it's called statistical sum. Which also represents the kind of essence of this term. So it's a normalization factor, right? So since all those contributions, product of positive, this is a positive number, it's number, right? So z doesn't depend on sigma, it's sum of all possible configurations, that's a normalization. Okay? So now what are problems which we are discussing? This is the simplest, this is two others, they're more or less of the same level of complexity or simplicity, depending on how you look at it. But first is, I want to compute most probable configuration, right? In other words, all those configurations have certain probability, and one of them may be, unless degeneracy, maybe 2, maybe 3, most probable. I want to know which one is the most probable configuration. So formally, I maximize P of sigma. Well, when I write this arc max, those who don't know this notation, is argument of max, which means that this outputs a particular value of this vector sigma. Okay? So, and this is obviously optimization problem. That's already here. You see, and of course, combinatorial optimization, right? Because I'm talking about discrete alphabet. At least, I mean, I said default it is binary, right? Well, integer programming, if you wish, type of problem. Well, there are different names. Most probable configuration, maximum likelihood, ground state. Ground state is in physics. Maximum likelihood is more like information theory, but that's all about the same. So now, second problem. Well, third. Let me jump to third. It's a computation of this partition function. It's counting, right? Partition function. Each state. Well, when I call state, it's a configuration sigma, configuration of this vector. Each state has a certain value assigned, and I sum over all those states. So I go through states and some contribution. In the first case, in principle, straightforward algorithm, straightforward approach. I go through all states and pick one which is most probable. In the last one, I really sum up configuration. So it's weighted counting. It would be counting if I put weight unity, but weighted counting, that's what partition function is. And will be discussion of complexity issues in this course quite a lot, and you can sense that this problem is probably more difficult than the first one in terms of how many steps required to answer the question, to get an answer. So question in the middle is actually closer to the last one. And question in the middle is the following. So I pick one particular h, so it's a probabilistic question. I pick one particular h, for example, but it may be, there are generalizations, but for example, h6, 7. And then I ask what is the probability according to this joint distribution function, multivariate probability distribution, which I already defined. What is the probability to have this h in a state plus or in a state minus? Obviously, if I sum them up, those answers will be unity, right? Because there are only two options for this h. So it's marginal probability. And formally, I sum. So this notation, hopefully it's familiar. So I sum with respect to all components of this vector sigma but one. And this one in this particular case is 6, 7. And it's also summation, but now summation of a restricted set of options, states, options, I guess it's a better word. In this sense, it is more or less can be thought as a computation of a partition function in a little bit redefined way, right? So basically, you fix a variable here, and then you kind of open up this edge, and then you have a remaining graphical model, and the respective object is nothing but computation of partition function in a little bit modified graphical model, but otherwise it is the same. Okay. So now let me. I guess I can. It's a generic blurb about where these things which I'm talking about, where they fit. Let me maybe take a minute on that. The point is that there are multiple disciplines which depends on this type of computation, so this type of evaluation. And if we go to top level, game theory, optimization and control, machine learning, they all more or less use it as a tool, what I'll be discussing. And I'll be discussing computations of this type of things within this graphical model. And again, graphical model is just a particular way of factorizing your probability, which is, maybe coming from domain, which you are working on. And I'll illustrate it. Maybe coming from physics, maybe coming from biology, information theory, etc. Right, so there is not much of information here, but just, hierarchy of relations. So That's why graphical models are kind of important and popular and well, cross through many disciplines. So now let me start from physics, and well, if you're a physicist, even if you're not a physicist, you probably heard about Ising model. I don't think there is a single physicist who never heard about that. So it's basically, well, we often say that it's Ising model of, which is basically says that it's most popular. And what is Ising model? Well, I'll not be telling you how it comes from magnetism. I just formally define. So it's usually describe magnetic properties of material. That's how it's originally appeared. And so there are spins, and spins may be up or down. Well, well, there are other situations, but this is quite standard. And then those spins interact. And interaction is expressed in this form, and probability of a particular configuration is therefore is stated as well. What is under exponent, actually minus of it, and also with added, temperature normalization. Physicists usually call energy of a spin system. For particular configuration of spins, that's what energy is. Translates and probability. Again, I'll not be explaining why and how. Why and how it's written here in a schematic way. Yeah. So in this particular case, you may ask where is the graph and how it comes. So graph in traditional physics, in standard, it would usually be lattice, either two-dimensional or three-dimensional, because it's usually about materials. Maybe materials with disorder. Not regular lattice, but that's traditionally where it came. And then those spins reside on vertices, and so here graphical model is a little bit different. All right, so variables are on vertices, and functions or relations are on edges. But I really can redefine it in the previous form. We can, let's keep it as an exercise for those of you who follow. We can get back to that if there is interest, but later. Actually, we'll not touch on Ising model today any longer. Yeah, so now there are various regimes in which this model is studied, and a specifically interesting regime when those JJs are, when they're very small. That's what in physics called high temperature model. And you immediately see that in a regime of very small J, basically all states, all configuration of this vector sigma are almost equiprobable. And that's one extreme. Another extreme is when J is actually rescaled and made very large. And then you effectively end up with either one dominant state, which is most probable, another much with probability significantly less, and that's so-called zero temperature limit. It's also important to, again, for those who are physicists, to distinguish some let's say, opportunity for me to emphasize a few things about what I'll be focusing on. In physics, people usually, researchers usually discuss so-called thermodynamic limit. When you have a lot of those spins, you're not considering one graph, you consider a limit of infinite graphs, so sequence. And sometimes actually also discussing averaging of so-called disorders, as JJ, considering all possible configurations of J. I'll not be discussing that in this course. Well, if there will be questions, we can discuss it offline, but I'm not planning to focus on that. So my questions will be mainly algorithmic. So for given graph, and not necessarily like in physics lattice, and for given JJ, if you're talking about this Ising model, how to do those computations which I mentioned. Partition function, most probable configuration, marginal probability. Interestingly enough, this Ising model penetrated to other disciplines. In particular, it's probably one of the most popular models of machine learning. And in machine learning, of course, there is no, well, at least in majority of cases, there is no direct reason to use this grid or regular structures. But usually it comes in the following way. So you have measurements, and measurements are binary, and you need to guess and you assume that those measurements, how we call them samples, are produced by some distribution function, and you assume some general purpose distribution function, and in fact, it's not most general, but I mean, if I add so-called linear magnetic field term, linear term and the exponent, that will be almost most general case when graph is not yet specified and this J's are not specified, and we solve inverse problem, which I'll show on the next slide, and that's roughly how it comes into machine learning. So this Isaac model appears to be generic in this regard. It's actually illustrated in here, so you may have one observations, then you may have another observation, and then you may compute averages or expectations at every point. So observations at the point, and then you basically well, you might ask a question: what is a graphical model behind? So you don't usually see it. So you solve this inverse problem. So threads is what you'll be defining, what you'll be recomputing, in particular from expectations, from averages. Sure.
What is written on edges? Is it maximal probability?
I'm not discussing how at this stage. We'll come back only the 6th lecture to some machine learning example. Machine learning is more difficult. Well, learning graphical model is solving inverse problems. So what I'll be discussing in practically, its main subject will be direct problem. So I know all those red value. I mean, I know graph and I know values assigned to each edge, and then I want to compute most probable state, partition function, or marginal probability. But hold it for whatever, for a few days.
Could you please one more time explain what's the difference between the direct and inverse problems?
Okay. Direct problem is direct problem is that. So my graph is given, my factors is given. So basically, my probability distribution is completely defined. But and I want to compute to answer those questions which I listed in here, was explaining. Okay, so that's a direct problem. It's still a difficult problem. We'll be discussing complexity of that. So inverse problem, well, interestingly enough, it's not always more difficult than direct, but inverse problem is opposite. I'm getting some marginal probabilities. Well, maybe situation when I have all of them, but in this case, for edges, well, usually inverse machine learning is defined when variables are on vertices, not on edges. But it's inverse in the sense that I have some marginal probabilities, but I don't know graph and I don't know factors, and I want to reconstruct those. But I mean, we will not be diving into that, at least not for now. Yeah, learning is inverse of inference. Learning, well, I should clarify, it's learning, so-called learning graphical models. Okay, so now back to direct problems, and that's actually a problem which brought me into the subject. So I got interested in information theory and well, specifically in error correction codes, and few slides will be about that. So in error correction information theory situation is like that. So you have your original data, or in original data is in general, but in we think about communication channel, let's say fiber optic channel, and we prepare what we call code word. it's maybe a sequence of those plus minus ones, or maybe something a little bit fancy. And then we send it to the channel. And channel is noisy, so this sequence of plus and minus ones, or pulses, will be modified potentially, and it happens probabilistically. So it may happen, I mean, each pulse may be flipped or not. And usually we have a model of a channel, and for example, we may say that each bit is potentially can be flipped independently on others. And then you're getting this corrupted data, which is x. You send sigma, you got x. And x may be from the same alphabet or from different alphabets. So it's like if you send plus minus pulses, I mean, stream of plus minuses, you may be getting, I don't know, 1.1, so it may be continuous. So it's really maybe analog measurement, or maybe discrete, it's already rounded to plus minus 1. And then you are facing this inverse problem, inverse in this setting, you want to reconstruct sigma from x. So that's statistical inference. So what does it mean? It's you want to compute a possible pre-image of sigma given x. So now let's see how we can possibly do it. So we can ask the following question. So you can take this probability distribution of transition from sigma to x, which models our channel. And then we may ask this argmax question, right? So most maximum probability, so most probable sigma which generated this x. X, we measure x, and we want to know which of all possible sigmas is possible. Well, in some cases we do this bit decoding, so we don't reconstruct the whole code word, but we reconstruct bit, and then exactly this marginalization which I mentioned before. Yeah, so that's right. So channel is a noisy black box with only statistical information available. Well, in coding I didn't tell you about that, but the sigma is usually constrained. So not all possible configurations are allowed, and this is prepared according to some code book, how we call it. And decoding, so answering this, solving this problem which I just showed you before, well, either this or that, is decoding, and that's where algorithm is coming in, and that's what we want to do. Those are examples of channels. Well, that's actually one example. It's a so-called additive white Gaussian channel. So transition probability from y, which supposedly is plus minus 1, to x, well, it's just Gaussian. So it's called white Gaussian channel. S is usually referred to as a, signal to noise ratio of this channel. And, okay, so graph, right? So how graph is coming? Graph is coming on in this particular application. Well, there is this. Well, what I sent to channel is a result of encoding, which I was not explaining. And graph is to a degree explaining relations between source, your relatively shorter vector of pluses and minuses, and all configurations of those pluses and minuses in a string are allowed. It's like, two encoders. So that's how a graph is entering into the game. Let me maybe, it's most frequently stated in terms of so-called parity check matrix. This parity check matrix, well, those are actually examples of parity check matrix. So it's a relatively sparse matrix. That's why we prefer to talk in terms of parity check. Well, 155 is one dimension of this matrix. But in any case, I guess, I don't know if I want to spend time on that. So maybe, let me see. Maybe we'll jump over that, unless, let's do the following. Let me not go into details with that, because it's kind of specific and probably deviate attention. from a main subject. But if somebody will, especially those who wants to work for credits, want to focus on this coding, there are plenty of problems in coding which we can discuss. Okay, so let me maybe not go into details for now. Details of coding. Right. Well, but basically, this problem of coding I can restate in exactly this format which I started from, and that's what I put in slides. But for now, I think it's probably better not to lose focus to jump over that. Okay. Maybe last application to mention. I basically want to wrap up this application and come to something. To conclude this hour with something a little bit more interesting already than just in general words. I don't know if any of you are interested or any of you heard about combinatorial optimization, but KSAT in particular, I'm guessing, well, you're smiling, I'm guessing at least some of you heard quite a lot. So there are a lot of, well, it's integer programming type of problem. So it's optimization problem in this regards. Well, I can formally introduce all these probability things, but normally when people are saying KSAT, they're focusing on most probable configuration. But problem is stated like that. So you have variables, vector x, and it consists of all those components x1, x3, etc. And you have this formula, which is written here as, so F is a conjunction of M clauses. M is each clause is a row, in the row in this expression. And basically conjunction means that either of those statements are true. So what does it mean true? So x1 is binary, and this V is O. So that's either of them is true. So now true means that x1, for example, is 0. So if x1 is 0, then it's true. If x1 is 1, it's not true. So in this particular case, this x1 or x2 or inverse of x3, this bar is inverse, means that a requirement is that this first clause requires that either x1 is 0 or x2 is 0 or x3 is 1. And then there is a union, end of all of those, right? So there are clauses and there are unions. So basically, a typical question is to, first of all, answer the question of if there exists a vector x which satisfies this formula, right? Which is basically all those statements are true. This logical formula is true. That's that's the first question you ask. In principle, you can also start doing, it may be a situation that there are no solution, right? Then, if you, you basically stop then, if you figure out how to answer, to certify that there is no solution. If there is solution, maybe more than one solution, right? And in this case, you actually, typically probability is assigned equal probabilities to all solutions. So this F, in this regard, is by itself is a 0 or 1. So 0 if it is not satisfied, and 1 if it is satisfied. But then you may really do this counting, not weighted counting, but counting of solutions. How many of solutions? Well, in principle, you can define this problem even when there are no solutions, then the answer will be 0. So therefore, you can, even though it's a bit synthetic, you can put this probabilistic interpretation too. So you can formally assign probability to each possible states, and state may be possible in the sense that you consider all of them, really all, and if state is not satisfied according to this formula, this F is basically is a 0 or 1, two-valued function. Okay, so finding valid assignment. Right, so usually this type of problems, so why they call KSAT, sorry. So in this, what I wrote in here is 3SAT because each clause has 3 variables. But the point is that variables are entering, if you look at this formula, this x1 is entering at multiple points, right? And x2 and all of them. And you represent it through the graph of relations. And usually, well, there are a number of graphical representations, so it may be, you can think of graph as a bipartite graph. And on one side you have variables, on another side you have clauses. So here variables, so 1, 2, etc., and then clauses. So there are m variables on the left and n variables on the right. And if a variable is connected to, is entering the clause, I put h, right? So this is the way how I introduce graph in this case. And again, I'm getting graphical model. In this case, I already mentioned this thermodynamic limit. People love to study this limit of m and n going to infinity, but ratio of m and n fixed. And depending on this ratio, there is this phase transition from satisfiable situation to unsatisfiable. Well, if you have m is a number of clauses. If m is small, obviously, well, it's not natural, let's put it this way, natural that you'll probably have quite a lot of solutions. But when m grows, you'll be in trouble, and apparently there is this critical alpha for which you're really in trouble. And but once again, I'll not be focusing a lot on this thermodynamic limit, mn going to infinity. Okay? Right. So for all those problems, and we'll get into details of some of them later on. We have these 3 basic questions which we'll be trying to answer, and again, it's a most probable configuration, marginal probability, partition function. And for all those questions, we have a graph, and graph will have size in terms of number of variables. In this joint distribution function, multivariate probability distribution, which the model will represent. And first question to ask is how many operations are required to evaluate graphical model. Answer to any of these questions. Then, what is exact algorithm with the least number of iterations? I already mentioned some exact algorithms, right? So when I was explaining partition function, I was saying that I have n variables, 2, and all of them are binary, 2 in the power n. I certainly can sum them up, right? But that's exponential, so can I do better than that? So obviously we are in the hunt for faster algorithms which scale well, and I'll talk about that in a second. So exact, right? So, sometimes when it is really prohibitively expensive, like I really cannot reduce this 2 in the power n to something, which scales better with the size. 2 in the power n, obviously, you cannot deal with on any computer when n is, probably already 1,000 years stuck. Well, even before that. So now, then you start asking about approximate algorithm. How to approximate to get approximate answer? And approximations maybe, there are different type of approximations. So we'll touch on that. However, main thing will be about exact. In this course, will be about exact algorithms. Okay. Now. In approximation case, there are different ways of evaluate. The quality of this approximation, and there'll be some measure of success. I'll discuss on all of that. And if approximate algorithm will be discussed, we often will be asking question: is it really? Actually, we'll be asking this question also for exact algorithm. What is the is it the best algorithm we can get? Can we make it better? And better in the sense again of scaling number of operations. I'm not defining it in a mathematical way at all, but jargon is that if it is linear in n, that's super easy, that's very nice, that's what we prefer. Well, if it is algebraic, it's still good. Well, even though if it is, I mean, n in the power 10, you're probably not happy, but at least formally it's much better than exponential. So exponential is difficult, and that's basically what you want to avoid by all means. And that's more or less will be in the focus, I mean, discussion of how many operations are needed. Right, so now, surprisingly, there are many problems which are easy. And when I stated as easy here, I really mean polynomial easy, not linear easy, even though some of them is. Well, first one, that's what we'll be discussing next hour. So we'll be discussing this case, which is remarkably good, when this graph which we are dealing with is a tree. Right, so will be quite a lot of focus on that in this course, and generalizations of what we'll get from this tree structure. So what is exact on a tree, how to extend it to other graphs. However, there are other examples which are probably even more remarkable. I don't know if you know about them, but hopefully you'll at least learn or hear about some of that during this course. Maybe most unusual thing is a story about planarizing model. So partition function of planarizing model, the sizing model which I showed you, and if you have a planar graph, planar means that there are no overhangs, so you can really project it to plane, and no edge crossed. It's easy. It's easy, so it's not exponential. Well, it may be pushed to n 2.5, but you may say that it's n cubed. Then ground state, or most probable configuration, is the same Ising model, but now not necessarily planar. However, it is what physicists call ferromagnetic and computer science is called attractive model. It's also easy, and there is a whole class of generalizations of that. We'll discuss it too. 2SAT will not discuss, so that's this K-SAT problem which I mentioned in satisfiability. Its 2SAT version is easy. Well, in decoding story, it depends on the channel. For certain type of channel, in particular this channel binary erasure channel, it's easy, and by the way, it also can be restated as a satisfiability problem. Basic network flow optimization algorithms. Probably you heard about max flow, min cut, shortest path. There are plenty of those. I mean, the family of these network flow algorithms. We'll touch on some of them. They're all easy. Easy in the sense of non-exponential. So it's actually, well, yeah, it's quite related to these three computations. Minimal matching problem. It's optimization problem. It's easy, and it's actually easy in a very non-trivial way, so we'll discuss it in relative details, so-called Edmonds algorithm, and there is some version of it which actually can be solved with the help of graphical model. Totally unimodal integer programming. In general, they're easy, and with graphical model representation also helpful. Yeah, so that's all of that. I put it, first of all, to flash some of the problems we'll be discussing, but also to say that it's quite non-trivial and encouraging, that we have a lot of problems which are you would naively say not necessarily easy. You would guess they're difficult, but they're in fact easy. However, that was encouragement, so this is kind of generic pessimistic statement. graphical models with loops and arbitrary, over arbitrary graph and with arbitrary factor functions are difficult. And well, if somebody will manage to show otherwise, all possible prices will be used, but we don't expect it to be true. And therefore, it's a lot of practical stories about maneuvering and finding, even, if you don't think in general you are easy, an easy world, probably somewhere close you have an easy problem, and finding this problem is actually, for finding this formulation is important. Okay, so now, well, since we started a little bit late, let me for last 10 minutes of this hour and then we'll call a break. Let me just, actually, I think, yeah, I'm already here, but I'll be actually talking for some time because there is quite a lot of information on this slide. Okay, so we are discussing partition function, right? We were discussing, and partition function was stated problem of computing partition function. I call it weighted counting. So I'm summing up configurations, and I want to know this normalization factor. And you would say that, well, it's counting. How this counting can be possibly related to optimization of some kind. And it is related, and that's what I'm trying to, I'm summarizing in this slide. So the story, well, those of you who already heard about Kubler-Leibler comparison of measures probably can see and start guessing what I'm trying to say, but it comes under this name, Kubler-Leibler in computer science, but in fact, it probably first trace of this type of formula is in the famous, Gibbs is well, more or less founder of statistical mechanics, and he had this very famous book. Well, 1903 is not first edition, but it's apparently already there. This type of statement, even though probably, coded in some other way. So now, okay, so what do I do, what I'm trying to do in here? I introduce a functional of what I call beliefs. And you remember that on the first slide, I'll not be putting, going there, I have this P of sigma, which is my probability distribution, which I stated in a factorized way, and that's how I introduce my graphical model. So what I write in here is a very general, it doesn't need to be, this P of sigma doesn't need to be factorized as a graphical model. But the gist of it is the following. So I start thinking about approximating or finding some proxy for my probability distribution. So I know P of sigma, and now I'm, well, and this P of sigma, just for, for a matter of, well, reference, is factorized. So you remember that P of sigma was product of A over A of A, FA, those factors sigma A, and I also had normalization, but let me drop this normalization, okay? So, and what I'll be doing, I try to come up with a functional in this case of this B of sigma. B's are my probe functions, which will minimize this function. Okay, so what this function is about? I probably can I go there and maybe start right here. Again, this P of sigma, I was writing it in this form, right? That was on the first slide, and unfortunately I didn't copy it as this slide. So now I introduce B of sigma, and B of sigma will be my proxy for P of sigma, right? And I'm introducing functional, and functional which depends on B of sigma. What does it mean? It means that I have sigma maybe, well, I don't know, I have this plus minus 1, so 0 ones. Let's say I have 0, 0, 0, so one state. Then I have 1, 0, etc. So there are many of those states. So sigma can take any of these. Let's say I have n variables, additional variables, which in my case were residing on edges, and I have overall 2 in the power n of possible sigmas. For each of them, I am assigning b, and I didn't fix this b, right? So b is a probability, so I want this b of sigma to be in between 0 and 1, all right? And I want to sum, in sum, b of sigma to be 1. Well, I can actually, of course, drop this 1. It just needs to be positive, and in sum should be 1. Because I want this b of sigma for my prop function to be probability. But otherwise, so that's a set of constraints for my optimization. Otherwise, what is written on the board is a functional which I want to minimize over this b of sigma constraint in this way. And what is actually written over there, you probably can see, is the following. So it's a b of sigma logarithm b of sigma. Well, I'm always confusing what is up and what is down. Yeah. And then here I put these factors. Well, basically here I wanted to put p of sigma, but p of sigma is this product of factors and also this 1 over z. So I drop this z from this formulation, right? And the statement is, so this is this functional. Statement is that if I'll be looking, well, I already wrote it here. If I'll be looking for minimum of this functional over this b of sigma under this set of constraints, what will I get? So it's a very straightforward exercise, and I really recommend to go through this exercise. It's very simple, useful, and if you understand it, it will be certainly pays off. So your optimal b, so let me call it b optimum of sigma, will be exactly p of sigma. So it's also easy to see that this functional is convex. And convexity, I guess we know what convexity is. Those constraints are convex. So it's a nice convex optimization problem. And remarkably, this at optimum, f of b optimum, is exactly a logarithm of z, this normalization. Oh, did I write it in there? No, I didn't, but that's what you'll be getting. So now, first of all, what does it help? How does it help us? I restated my problem of counting as optimization problem, right? I now say that, well, instead of counting, you need to solve optimization problem. And optimization problem is convex. Well, you may say that that's it. We shouldn't discuss it any further, but I guess there is still a catch, right? And can you tell me what is a catch? Why? Well, it's useful, maybe representation for some evaluations, further evaluation, but still it doesn't solve my problem, right?
Okay, binary variables, how do we optimize that?
Well, I replace my binary variable. So now I have continuous variables. So variables, those b's of sigma, they're all between 0 and 1. And there are, well, I guess what I wanted to hear is that there are 2 in the power n of them. There are exponentially many variables. And I did reduce my original problem, which was counting over 2 in the power n variables. Now to optimization over, in fact, 2 in the power n minus 1, because I have one constraint, right? So I didn't gain much in terms of, I still have a complex problem. Now I have too many, not only, so I have optimization, continuous optimization, instead of counting. but over too many variables. However, so that's kind of, on one hand discouraging, but on the other hand, it's very important formula for many other things which will follow, because it's very generic, and because when anything restated as optimization, there are multiple ways of going around. And another, maybe to stress it one more time, it also illustrates how you transition from discrete to continuous in a very, if you wish, intuitive and physical way, and also in probabilistic way. So you go from your states, from your discrete variables to continuous variables, which are probabilities. In fact, you can also do it for continuous variables, and we may discuss it later today. We'll see. So I have it in the slides, but I'm not sure we'll get it. So let's call a break, maybe for 15 minutes, and then we'll continue.